Chapter 1, we have learned on the approach, the principle, the steps, okay, the sequence. Now we move in details on the process synthesis part. Okay, so in chapter 1, as we recall, the process synthesis. Okay, process synthesis, where these 5 are important for you to memorize and understand. Okay, the first step is to eliminate the differences in molecular type, where here it involves the chemical reaction. Steps 2, mixing and recycle to distribute the chemicals. Means what are your input, your feed, your product. And then identify what are your waste. Perhaps what are your inert. Okay. Then separation, how to separate your products, your waste. Here it means to eliminate differences in the composition. Okay, then the temperature, pressure, and phase change. Each of your unit of what are the temperature, pressure, and phase change. So is there any specific unit operation for you to use to perhaps change the phase, increase the temperature, okay, reduce the pressure. Then after those 4 complete and finalize, then only you do the task integration. Combine everything into one KFD. Okay, into units operation. Combines all those unit operations. Okay, chapter 2 will deal with heuristics rule. What does it mean by heuristic? The term heuristic. What is heuristic? Anyone? Heuristic. What is heuristic? What is heuristic? Don't just look at me. I want answers from you all. What is heuristic? In first chapter 1, hierarchical. We follow the hierarchy, the rank. Now heuristic, what does it mean? Huh? Yeah. Try and error. Yes, correct. Shortcut. Simplify the method. Okay. That one can be done through experience. Okay, those heuristic later on when you see, those are generated from experience. Okay, and also in general concept. Now, why the heuristic is important? It is to expedite the selection and positioning of the process operation. Okay, to expedite. But this heuristic should be tested, usually by simulation. Okay, should be tested to validate it, whether it is feasible or not. Okay, now we will move one by one of the process synthesis step. Okay, these are again the steps. Now we move to point number 1, which is the eliminate differences in molecular type. It means it involves your raw materials and chemical reaction. Okay, this one involves in selecting the alternative process. selecting or selection of alternative process. Heuristic 1. Okay, select raw materials and chemical reactions to avoid or reduce the handling and storage of hazardous and toxic. Okay, usually we focus on hazardous and toxic raw materials. Okay, we have here example of manufacturing of ethylene glycol, EG. This is the product, ethylene glycol, okay, EG. Now, from this reaction, EG is produced by reaction 1 and 2 in series. So, from the raw material, ethylene, okay, ethylene react with O2, oxidation process. It produces an intermediate product. This intermediate product, ether. Okay, so this intermediate product, ethylene oxide, is highly exothermic. Sorry, both reactions are highly exothermic. But a water spill into an ethylene oxide storage tank could lead to an accident similar to the bhopal. So this ethylene oxide intermediate is hazardous. And the condition is not stable. It must avoid any water spill. Okay. So often the process designed with two reaction steps with storage of the intermediate. So the first reaction, you have this as your intermediate, ethylene oxide. This one will go to storage to enable continuous production. Okay, even when maintenance problems shut down the first reaction operation. So this ethylene oxide must go into storage first before it proceeds to reaction 2. Okay, so here, this storage, you must have specific design in order to secure this ethylene oxide. Okay. And the storage is required because here, as it mentioned, if the first process shut down, the first process line shut down, you still have the storage to supply to reaction 2. Okay. Now, alternatively, since this one is hazardous, risky, it can explode if contact with water. So you need to think any alternative process that can produce ethylene glycol. So this one of the alternative to the two-step EG process. Okay, it's either eliminate the storage tank that causing intermittent interruptions when the oxidation reaction shut down. Okay. Other alternative is to use chlorine and caustic in a single reaction to avoid the intermediate. Okay, so this one can be your alternative reaction, reaction 2, that you can consider. Okay, this one, reaction 1. Let's say this one is as reaction 1. Reaction 1. This one, reaction 2. Okay, or as the ethylene oxide is formed, the intermediate ethylene oxide, react it with carbon dioxide to form ethylene carbonate. Okay, react with CO2 to form ethylene carbonate. which is less active. Okay, so this one is less active. Another intermediate then react further to form the ethylene glycol. Okay, so this one, reaction 1.2. So this one continuous from reaction 1 just now. Okay, reaction 1. Here, reaction 1. The intermediate react with water, H2O, to form EG. Since it is risky, so this intermediate react with CO2 to less active intermediate that can be stored safely. Then from here, react to form EG. You have one additional intermediate. Okay. You don't need to memorize this reaction. You need to understand the steps. Meaning that this step 1, the raw materials and chemical reaction, you need to have a few alternatives for you to consider. When it involves the toxic, hazardous, and risky operation. Okay. Ken, any question? Understand? Now, next one is the distribution of the chemicals. Okay. Okay, distributions of chemicals. This one is the second step. Ignore this number 1. This one from the previous slide. Don't know why it continues here. Okay, number 2. Distribution of the chemicals. Identify what are your input, output. Input can be your raw materials, catalyst, inert. Output can be your product, byproduct, waste. Okay. Now, heuristic 2, use an excess of one chemical reactant in a reaction operation to completely consume a second valuable toxic or hazardous chemicals. Okay, here it means that in this reaction, the VCM reaction last time, let me make it bigger. In VCM reaction last time, we have C2H4, ethylene, and Cl2. Cl2 is toxic and hazardous. Okay. What does heuristic 2 means? Ethylene oxide supplied in excess so that it can consume fully, completely on the chlorine. Okay. Why we need to let the ethylene consume completely the chlorine because we don't want the chlorine gas to be released as the waste or byproduct. Because Cl2 is toxic and hazardous. Okay? Get the point? So from here, from this PFD, you can see chlorine is completely converted to the main product, VCM, and also the byproduct, HCl. There is no chlorine gas release. Okay, no Cl2 release. Okay, any question so far? Yeah. Now, heuristic 3 for distribution chemicals. When nearly pure products are required, eliminate inert species before the reaction operation. When the separations are easily accomplished or when the catalyst is adversely affected by the inert. Do not do when a large exothermic heat of reaction must be removed. Okay, when large exothermic heat means there are at high temperature, high heat release. Okay. Now, what does it mean here is from this. Why the writing here then still there? It moves together. Okay, just ignore this. Now, what does it mean is from here you can see. Let's say, for example, we have A and B as the feed, E, F as the product. Another feed here is impure. Okay, impure. So for reaction 1, A plus B, you get the product. Reaction 2, A plus C, you get the product as well. So D here, you see, D is D involved in the reaction. No, right? So what does it mean? What D is doing over there? Huh? Impure feed, yes. Then D is not reacting. So D is the inert. It doesn't involve in the reaction. So we call as inert, right? Then, okay, here, the statement over here, nearly pure product are required. Eliminate inert species before the reaction. So the impure feed over here, since we don't need the D, separate the D before the reaction. Because if you don't separate the D, you might have D in your product stream because it is inert. Okay, so that's why you need to remove D before the reaction. Sorry, don't know what happened. Cannot be erased. Okay, you get another point. In this case, remove D if you need pure product, since D is your inert. Okay, in this case, D can be removed at initial stage. Okay, there are cases that inert cannot be removed at initial stage. Okay, we go case by case. Okay, let me close this, open and reopen, because the thing does not disappear. Wait, give me some time. Okay. Here, heuristic 3 just now. D is the inert, which is not involved in the reaction. So separate before, yeah, the decision is required whether to remove D before or after reaction 2. If you don't remove before, you will have inert in your product. So if you have inert in your product, then over here, you need to do separation of the D. Okay, it's either removed before or after, case by case. Okay, here it shows you the example. If you remove before, okay, here is the case when you remove before the reaction. Here, when you remove after the reaction, okay, it involves the cost of separations. So you must assess cost before and after. Which one is more feasible? This also can be accomplished by examining the physical properties upon which separation are based. Okay, and you can use simulation. Okay, in the case of highly exothermic reaction, see the note over here. For exothermic reaction, the inert species absorbs some of the heat generated. Okay, so it lowered the final temperature of the reactors. So in specific case, you need to supply the inert to absorb the heat so that the temperature of your reactors can be lowered down. Not at high temperature, which later on you need to use heat exchanger to reduce your temperature. Okay. We'll do example after we covered all the steps first. Okay. Now, still on the distribution of the chemicals. Step 2. Heuristic 4. The next heuristic. They introduce liquid and vapor purge streams. Liquid or vapor purge stream to provide exits for species that enter process as impurities or produced by irreversible side reaction. Heuristic 4 talks about purge stream. Okay. Heuristic 3 just now, it talks about the inert. Okay, now. Purge stream for these impurities or produced by irreversible side reactions. When these species are in trace quantities. Trace quantities means in low quantities and or difficult to separate from other species. Okay, remember that I shared with you in chapter 1 the recycle system, about the recycle system. Okay, just let me share you again. Now we are talking about the purge stream. Here. This one. Okay, here it has the purge gas stream. Separate the purge gas stream. Okay, perhaps this, in this case, it purge out the syngas. Purge out the CO2, CO, and it separates the H2. Okay, so why it needs to purge out? Because if you don't purge out, it will accumulate in your stream, in your system. Okay, so here the purge gas, last time we discussed, is the CH4. Because up here, flare gas. Okay, use flare. So over here, perhaps the CH4 is in trace quantities. Trace quantities mean just a small quantities. If you don't separate, it will accumulate in your system. If you want to do a specific separation, it will involve cost, whereby your methane is just a few percentage, not feasible. So that's why they choose to flare the methane, because in low quantity. Okay. If in your byproduct, let's say this methane, if it is in high composition, let's say perhaps you produce 40%, then it is feasible to separate it and to store and sell rather than flare it. there are conditions that you can study, the cost effectiveness. Okay. Let's say you produce CH4 around 2%. So no point you want to dump a lot of money for a separation system for just 2% of methane, right? Easier just to flare the gas. Okay. Now here it gives example of ammonia reactor loop. Ammonia reactor. Okay, where the reaction to produce ammonia, you need N2 and H2. Go into a reactor. Okay, then after the reactor, you have ammonia and perhaps N2, excess of N2. It also one of your feed. Okay, excess of N2. So that's why over here it use flash vessel to separate the ammonia and to purge out the excess of N2. Another possibility, you can recycle this N2. If the purge gas here is N2 lah. Okay, where you need the N2 in your feed to react with the CH4. Okay, or trace. Wait, I repeat my statement. Okay, that is feasible. But in this case, N2, H2 is the main feed. Okay, I start again. N2 and H2 is the main feed. Now, in the N2, it has some trace of AR. What is AR? Huh? Argon. Argon. Okay, argon. And then in H2 stream, you have trace of methane. Trace means just a small amount, small percentage. So the stream is not pure. Now it goes into the reactor, produce the main reaction, NH3. Now remember we have trace of argon and CH4, which is not reacting. So in your product stream over here, you have NH3 plus the argon plus the methane. Traces of these gases. You need the pure NH3. So the product stream being fed into flash vessel to separate the traces of argon and CH4. Okay, so purge over here, it means the argon and CH4. Possible? Argon, can it burn? Argon. Huh? Argon. Can argon burn? Noble gas. Inert. Group 7. Which group? 8. 8, right? Group 8. Argon, group 8. Organic chemistry, periodic table. Okay. CH4, yes, you can burn, flare. But argon is inert. Okay. So here you can decide whether to flare or what to do with your purge gas. Okay. Argon same group as N2, right? Is it the same? No. N2 which group? N which group? 7. sure 7? Check back the predict table. 5. 7 is atomic number. Group 5. Same group as chlorine. Again. Check back. So from there, that's why it is important. Okay, that's why it is important for you to know the properties of the gases that you produce. Whether it can be flat, whether it is an inert, or whether it can be liquefied or cryogenic. Okay, it depends to the properties. Okay. Any question? Can Okay, last slide. We go to last slide. Heuristic number 5. Do not purge valuable species or species that are toxic and hazardous, even in small concentration. Okay, do not purge. Just now purge, now do not purge valuable species or toxic and hazardous, even in small concentration. If toxic and hazardous in small concentration, if you purge, what happens? Impurities in the feed. If recycled, that can be one of the reasons. Corrosion, it depends to what type of gases. Okay. Let's say like chlorine gas just now. Chlorine gas, it is toxic and hazardous. Even though it is in small concentration, then you purge out to the environment. Even though small concentration, but your plant operating 24 hours. So imagine how much of Cl2 accumulated in the air if you purge them. Okay. Okay, so that one focus on valuable, toxic, and hazardous. So you need to add separators to recover the valuable species or add reactors to eliminate the toxic and hazardous species. This is not limited to these options only. Okay, you can have other options if you think can solve your issue. Okay. For example, here it gives a catalytic conversion of combustion effluent. Exhaust gas from internal combustion engine. Okay, you have CO, H2O, and NOx. This is toxic and hazardous. Okay, NOx. Now they install catalytic converter to convert the hazardous NOx, CO into CO2, NOx into N2 plus O2. Okay, so you need to find out what are the options that meet the sustainable design pillars. In this case, it adds on one additional reactor to convert the hazardous to non-hazardous gases. Okay. Any questions so far? We are at step 2 only, distribution. Have 3 more. 3 more main steps on the process synthesis. Okay, any more questions? Sorry, any questions? Okay, if no questions, I stop here. Tomorrow, I will continue on this heuristic 6. Okay. Okay, thank you. So for those who haven't scanned for the attendance, can do it this time. Wait.